Okay, so we spoke about the PCA being a mechanism to reduce the dimensionality of the data set. And the way this is done is by creating these hypothetical axes that better describe the distribution of the data, like we saw with the spring. So if I have an original matrix, X, and X, remember, it's a vector, it's a matrix of, we're talking about vectors now. We have an m times n matrix with x1, x2, x3, x4, n. I can apply some sort of linear transformation to that matrix, which means I can rotate it and stretch it using additional vectors. So a vector that tells me how to rotate my data, the eigenvector, and how to stretch my data, the eigenvalue, to get a new matrix Y, which is a re-representation of that X data set. Okay? So this is where the math gets tricky. So we have the vector xy, x1, x2, x3, x4, xn, so all the dimensions. And I am dot product, I am multiplying it by this new set of instructions. So I have to generate these new principal components of the data. So now I don't just look at x1, I have the dot product of x1 and p1 and x2, p1 and x3, okay? And remember, the dot product basically tells me it's how much of x1 is projected onto this new direction, into this new vector. So I have the rows of P, P1, P2, P3, P4, and Pm, all the way down the matrix, are the principal components of this matrix. And this is my new projection of the data set. So if these were my previous cameras, these are the instructions how to rotate these previous cameras to, and make them closer or further away, to generate a new set of coordinate systems that describe better the motion of the spring. So how do I generate these? How do I re-represent my X data set into Y? What's the best way to do this? And that really depends on what do we want from Y. So in the case of the spring, or mainly in all the cases that we talk about, we want Y to give us as much information as possible. So I want to see the spring moving throughout its entire journey so that I can work out the motion and how it relates to time. So I want to capture the entire variance of the movement of the spring. I don't want the spring to move and me not to see it. Okay, so if I want to best re-express X, that means I want a Y matrix that describes the highest amount of variability in the data. And that is called the variance. So we're going to use the variance to work out this new axis. And we're going to do it like this. What you see here are measurements of petal width. So we're talking about a really famous data set, the iris data set, which is a data set used in a lot of coding kind of exercises. And basically it's a data set of, I think they measured 3 species of flower, and they measured a few different parameters, the petal width and length and the sepal length and sepal width. So all sorts of parameters of the flower, and now you understand what a multivariate data set looks like, because they didn't just measure one thing about the flower, they measured a few different dimensions. So here are the two plotted against each other and how they vary across along each other. And we have the petal width and the petal length being quite correlated to each other from what we're used to. Okay, and I'm looking for something that's called the signal to noise ratio. So if I look along this axis, this dimension that I haven't actually measured, it's not the width and it's not the length, it's some sort of combination of the two. Along this red axis, I have the most variation in the data. Now at 90 degrees to that, I have some noise around this new axis. So if I thought of measuring this width and length of the flower, actually I'm capturing only some of the variation. The true variation, highest amount of variation, is actually sitting in this hypothetical camera, okay, or axis, that now we are starting to understand that if I rotate the width and I rotate the length a little bit, I can get something, a new vector that looks like that one, okay? So what my analysis is trying to do is to maximize the signal to noise. So to capture as much variation I can in the data while reducing the amount of noise around this axis. So a few things we need to do when we reduce dimensionality, okay, because that's the point of the PCA. I want to reduce the dimensionality. I want to deal with less. I don't want a spreadsheet of 500 different species. I want to deal with something else that's smaller. Then first of all, I need to work out which cameras are giving me exactly the same information. Which ones are redundant? Do I really need both of them? Okay, or can I generate something that is combining the information from these two in one camera? And how these two vary together is called the covariance. So if these two are showing me exactly the same thing, the covariance is going to be very high. If these two are not redundant, but rather are giving new information, in the covariance matrix, when I compare the covariances of all these different cameras, I'll find that these two have very low covariance. Okay, so the covariance is the measure of strength of correlation between two or more sets of random variables. So we do it between two, but it's in a matrix. So it's like when you saw the distance matrix between cities, right? Between Sydney and Canberra and Brisbane, and and you can have it in a matrix, but really each box is a set of two. So if we have a really strong covariance between two variables, it means they are very redundant. I mean, so really to capture that information, I should measure one or the other, or some sort of combined feature, but I really don't need both of them in the data set. Now, if I have n variables, so x1, x2, this is multivariate. So in the case of the iris, they measured 4 things. That the matrix is the covariance between all possible pairs. And remember, the covariance, when we first talked about statistics, is how each measurement varies from the mean on the I and on the J axis. So it's what I get now is going to be an m times m, depending on how many variables I have, matrix. And by symmetric, I mean the distance between Brisbane and Canberra is the same as the distance between Canberra and Sydney or Brisbane, whoever it was that I said. So we have a covariance matrix that is symmetrical. So anything, and it has diagonal terms and it has off-diagonal terms. So the diagonal terms are those that go down the diagonal, and off-diagonal are in those two triangles to the sides of that diagonal line. The diagonal gives me the variance between the variable and itself. So it's actually just the variance of that of that variable. So if I had variance in the petal or sepal length, then that is the variance I'm going to see in the diagonals. In off-diagonal terms, I have the covariance, or how those two vary together. So in the low redundancy data set, my off-diagonals are going to be really low. In a high redundancy matrix, my off-diagonals are going to be very high. And remember, the negative or positive doesn't matter here. It just means it's a negative correlation or a positive correlation, but they vary together in a predictable manner. So here I have, in other words, the variances in the diagonal, the covariances in the off-diagonal. So I look at the variations. So of course, each mean has a variance around it of beta 0, beta 1, and theta here. So these are those variances, but we're also interested in how they co-vary with each other to find redundancies. So what do I want to do if I want to optimize the cameras I'm using? Really what I'm trying to do is reduce this redundancy. I want to bring my covariances, I want to bring them to 0. I really want each camera to tell me its own unique story. So what I do is optimize the covariance matrix. Okay, and how do I do that? I start rotating things. So in an ideal case, and I'm not going to achieve an ideal case, but in the ideal case, all the off-diagonal terms are going to be 0. And by that I mean the matrix is diagonalized. And this is this orthonormal matrix P, okay, orthonormals at 90 degrees matrix P, where I'm getting my rotations from, is telling me how to rotate the data so that this covariance matrix is down to 0. So each one of these sets of instructions is a vector, and it's called an eigenvector. And another so it's an eigenvector of the covariance matrix. We're not going to talk about it in too much detail here because this is a little bit off the main path here, but we have principal components of X. P1 is the first principal component, P2, P3, P4. We're going to call the principal components. So what I want to do is find an orthogonal matrix, okay, where P gives on and X together give me Y, so that the covariance matrix of Y is now diagonalized. Okay, so that is the whole point of these principal components or eigenvectors. So the rows of P are the principal components of X, and each row of P is an eigenvector of the covariance matrix. So we have A1, A2 as elements of vector A, the eigenvector, and then the variances of A times X is maximal. And it's using Lagrange functions, and it's beyond how we're doing this. But what you need to understand is that there are principal components that rotate the data we have to generate a new matrix which is hopefully diagonalized.